Hey everybody, Greg here. How are you this evening? It's Sunday, November 22, and it's a pretty cold, dry day in Oregon. Got some bike riding in, felt really good. Was a tough day in the NFL, but you know, statisticians don't cry. They just accept the results and move on. So here we go. And I want to wish everybody a happy Thanksgiving. We all certainly have a lot to be thankful for. So just a couple of thoughts on last week. I think it went pretty well, and everybody seemed to do a pretty good job of getting it. We got a little more work to do on the hypothesis testing. One of the issues that came up that somebody asked was, we developed scales this week for teacher satisfaction. These were pretty minimal, designed to be used for exercise purposes. When you're going to actually do research, you're going to probably use an off-the-shelf scale. And when you look in the educational and psychology literature, there are scales for everything. There are scales for special ed, there are scales for attitudes, there are scales for virtually every attribute of human behavior, because you have to take a construct like teacher effectiveness and you have to operationalize it. And the way you operationalize it is by creating a scale that then the scale can have a value. So you've operationalized teacher effectiveness. In the same way, IQ is a construct. And so we operationalize the construct by creating a scale with 100 questions on it or whatever's on it, I don't know. And so you create a single point variable, but you'll probably be using lots of off-the-shelf, already developed scales to measure constructs in groups, and then you do your research based on that. One of the questions that came up was the p-value in the CTE study. That applied to the reliability of the scale itself. So that was done before the research. So there are statistical techniques, Cronbach alpha, KR20, that look to see if the scale itself is a reliable measure of the construct. So we know that the IQ test, as it stands, is a reliable measure of this construct called IQ. We don't know how valid it is, but we do know that it's reliable statistically, meaning you should get about the same, you should answer about the same thing on all of the questions. So it's pretty deep, but we don't get into the reliability of the instrument itself. That's for another stats course. One other thing that I wanted to mention was, when you're rejecting the null hypothesis, you're not accepting the alternative, and for this reason. Let's say you believe that the mean test score of 100 students is 50 on an assessment, and you take an example, or you take a sample of 49 students, and you find that the mean of the sample is not 50. Well, then you conduct the test and you reject the null hypothesis. What's the reason why you can't accept the alternative? Because there's still one person that was not in the sample which could deviate enough to mean that the null hypothesis still could be what you think it is. All right, so you can never accept the alternative unless you had a sample that was the size of the population, and then you wouldn't need to do any inferential statistics. Okay, so that's the reason for that. But I think everybody's starting to get the hypothesis testing. And the one thing is, one person put in theirs, they created an alpha of 0.01 instead of 0.05, and that's perfectly acceptable in research. That means your standard for rejecting the null hypothesis is higher. You have to have a much lower p-value or a much smaller probability of committing a type 1 error. The question always is, well, why is the p-value, why is the alpha set at 0.05 versus 0.01? Well, a lot of it has to do with the application. If they're testing the effects of a new drug that's going to be put on the market, they want to have they want to reject the null hypothesis that there are side effects. Okay, so they want to reject the null hypothesis that there are side effects in favor of the alternative that there are no side effects. Well, if it's a drug that deals with life and death issues, they would want to set the alpha pretty low. Okay, so that's the reason for that. But by default, in all research, psychology, education, it's at 0.05 unless otherwise specified. And if you want to set your alpha at a different level, there's usually only three, 0.1, 0.05, and 0.01. Then you're free to do that. You just explain in your research your rationale for doing it. And then if your p-value is less than any one of those, you reject the null hypothesis. Okay, so this week, week 5, we get into what's called multiple statistical tests. Now, this week is pretty straightforward again. You'll be doing more hypothesis testing. So you'll do some more one-sample hypothesis testing, which you're pretty comfortable with now. Then you'll also go into a two-sample t-test and an ANOVA test. And here's what they are. A two-sample t-test seeks to see if there's a difference in the means between two populations. So, let's say I have the length of the tails of the cats in Oregon over here and all of the cats in Washington over here. And I want to see if there's a difference in the mean lengths of their tails between these two populations. So I pull a sample of the cats from one state and a sample of the cats from the other state. And my null hypothesis is that the mean of the tails from each group is equivalent. My null hypothesis is that the mean of the tails is not equivalent. Okay? And again, since this is a two-tailed test, we're not saying that the mean of the cat's tails in Oregon is larger than Washington. We're saying they're either equal or they're not. Now, you can also set up one-tail, two-sample t-tests if you so desire. It's a little more complicated, but it's the same principle, and we don't get into that in this course because it's just a matter of making some adjustments, but it's the same concept. So we'll be studying two-sample t-tests, and you'll be using the QuickCalcs calculator again. It's almost the same thing, and then you'll report it almost the same way. The way you report a two-sample t-test is now you have a different number of degrees of freedom. You have the total number in both samples minus 2. So if your sample was 13 and one sample was 10, the samples don't have to be the same size. So that would be a total sample size of 23, so your degrees of freedom would be 21. But QuickCalcs will figure that out for you, but when you report it, you will have to have a degrees of freedom of 21. And I'll give you an example of how to report a two-sample t-test again. The other thing we'll be doing this week is called an ANOVA. Now, what an ANOVA seeks to do is to see if the means of 3 or more populations are equivalent. That is called a one-way ANOVA. And so the null hypothesis is that the mean of the cat's tails in Iowa is equal to the mean of the cat's tails in Nebraska, is equal to the mean of the cat's tails in Florida, is equal to the mean length of the cat's tails in Oregon. And if any one of those population means is not equivalent to the others, then you will reject the null hypothesis. And you do that by taking 4 samples, 3 or more samples from 3 or more different populations. Okay? So the two-sample t-test and the ANOVA are used quite often for comparison research. And they're pretty simple to use. They work pretty well. The calculators we have for them are pretty efficient. They do the job. They're easy to understand. And that's pretty much how this week will go. So we want to make sure we report the results correctly and that we indicate the conclusions correctly. And everybody did a really good job on indicating the conclusions. And some of those one sample t-test assignments were really clear. I really appreciate that. So we're off to another week. Yes, it's Thanksgiving, but we have to push on through. And got about 3 more weeks to go. I'll be home every evening except for tomorrow night. So thanks for everything and have a good week. Okay, bye.